Today we will continue with our discussion on unsteady state heat transfer. In this class, I will explain the usage of Heisler's chart in solving unsteady state heat transfer. As all of you know, when the internal resistance is negligible, the temperature distribution is uniform within the body and we can assume lumped heat capacity analysis. For this, White number should be less than 0.1. When the internal resistance is considerable, the variation of temperature within the body cannot be neglected. Now the temperature can vary with x, y and z direction. But in a very simple case, the temperature varies only with x direction and time. So if the temperature is only varying with respect to one of the spatial coordinate and time, it is also unsteady state heat transfer. But temperature is only varying with respect to one of the spatial coordinate, and in such a case you can get an analytical solution in the form of a Fourier infinite series solution. By truncating the series, you can have a graphical representation, and this is Heisler's chart. So Heisler's chart gives a graphical solution by truncating the infinite series solution to one-dimensional unsteady state heat conduction. And this chart restricts its applicability to Fourier number greater than 0.2. In lumped heat capacity analysis, the characteristic length we have defined for different geometrical shapes. For the flat plate, it was thickness by 2, and for a cylinder, it was outer radius by 2, and for a sphere, it was outer radius by 3. In case of Heisler's chart, the characteristic length is little different. It is different from the characteristic length used for lumped heat analysis in case of cylinder and sphere. And we are here talking about infinite plate. Why it is infinite plate? Because the temperature should vary only in the thickness direction. So if it's infinitely large, there will not be variation in the other directions. The shortest distance from the midplane of the plate to the surface is half the thickness. So from the center, the shortest distance for the heat to conduct will be half the thickness. That makes it one-dimensional. The heat conduction will be one-dimensional. The other directions, heat cannot conduct because the distance is too large. So the plate is infinite in size. Only thickness is finite. So in that case, from the center, the heat has to conduct only towards the surface. So it makes it one-dimensional heat conduction. Same is the case with the cylinder. From the axis, heat flows in the radial direction only. It will not flow in the axial direction since it is infinite cylinder, very long cylinder. So to the surface, the heat flow will be along the radial direction. In case of a sphere, the heat flow will be in the radial direction. Now, the characteristic length while using Heisler's chart for an infinite plate is thickness by 2. For an infinite cylinder, usually the characteristic length is taken as outer radius, and for a sphere, characteristic length is outer radius. So it is not R0 by 2 and R0 by 3. For cylinder, infinite cylinder, it is R0. And for sphere also it's R0, characteristic length is R0. So that difference you should note down. Now let us work out an example. A 5 cm thick iron plate with thermal conductivity 60 watts per meter Kelvin, specific heat 460 joules per kilogram degree centigrade, and density 7850 kilogram per meter cube, and alpha, that is thermal diffusivity, 1.6 into 10 raised to minus 5 meters square per second, is initially at 225 degrees centigrade. Suddenly, both the surfaces are exposed to an environmental temperature of 25 degrees centigrade with a convective heat transfer coefficient of 500 watts per meter square Kelvin. Calculate the center temperature at T is equal to 2 minutes after the start of cooling. The temperature at the surface at T is equal to 2 minutes after the start of cooling. The energy removed from the plate per meter square during this time. So you are given a 5 centimeter thick plate, assuming it is a very large plate and the size of the plate is not given. So let us take it as a very large plate. So its thickness is 5 centimeter. Thermal conductivity, specific heat, density, thermal diffusivity, and initial temperature and ambient temperature, heat transfer coefficient, all properties are given. You need to find out the temperature at the center 2 minutes after start of cooling, and also the temperature at the surface at the same point of time, that is 2 minutes after the start of cooling. So first two part of the question is to find out the center temperature and surface temperature after 2 minutes. Starting it was 225 degrees centigrade. Starting the entire body was at 225 degrees centigrade. Center and surface, initially it was 225 degrees centigrade. Now after 2 minutes, what is the center temperature? Center means mid-plane, that center plane temperature, and also surface temperature at the end of 2 minutes. So in the question itself make it clear there is a difference in center temperature and surface temperature. So non-uniformity in temperature. So temperature is not uniform. So you cannot apply lumped heat analysis. The question itself indicates that you cannot use lumped heat analysis. You should go for Heisler's chart in solving this problem. Also, we need to find out the energy removed from the plate per meter square area during this time. That is first 2 minutes. Again 2 minutes. So the first 2 minutes, how much amount of energy is removed from the plate. Now we need to use the Heisler's chart in solving this problem. In Heisler's chart, there are 3 charts. So first we need to find out the center temperature, that is mid-plane temperature. That is mid-plane temperature difference. There are 3 quantities here, like the mid-plane temperature difference will denote by theta 0. Initial temperature difference will represent by theta I, and temperature difference at any instant at a given point will represent by theta. So let us calculate the characteristic length. Characteristic length is thickness by 2, which is 2.5 centimeter. 5 centimeter is the thickness. So you get 2.5 centimeter. That means 0.025 meter. Now you can calculate the byte number. Byte number is HL by K, which is 500 into 0.025 characteristic length and divided by thermal conductivity is 60. You get the byte number as 0.2083. Now in using the chart, we need the quantity 1 by byte number. So I will calculate the 1 by byte number, that is the reciprocal of byte number, which will give 4.8. And also you require Fourier number. So Fourier number is alpha t by L square. Alpha is given thermal diffusivity 1.6 into 10 raised to minus 5, and time period for 2 minutes. 2 minutes means 120 seconds. So the time period is substituted, and the characteristic length we know 0.025. So substituting that, you get the Fourier number as 3.072. So we need 2 parameters in calculating the mid-plane temperature from the chart. Okay, so we need 2 parameters. One is 1 byte number and another one is Fourier number in reading the chart for mid-plane temperature. Now this is a chart showing the central line temperature for an infinite plate of thickness 2L. Okay, corresponding charts are there for infinite cylinder and sphere. So this is one of the chart out of the 3 charts for infinite plate. 3 charts are there for infinite plate, and similarly cylinder has 3 charts and sphere another 3 charts. So all similar charts. So we have Fourier number you have calculated. Fourier number is 3.072, and 1 byte number also we have calculated. It is 4.8. Okay. So 4.8 and 3.072. Now 3.072 will come somewhere here, and 4.8 will somewhere here. But this portion is taken and magnified and shown. Some of the charts will show like this. Okay, this portion, because to read accurately, clarity will not be there for this chart. So this portion is magnified and shown here. So 3.072 almost 3, and 4.8. This is 3, and this is 4, and this is 5, and this is shown as 6. So this line is 6. This is 1 by byte number. This for constant value of 1 by byte number, that is K by HL. So this is 5. 5 line is here, byte number 5, and this is we need 4.8. So between 4 and 5 and very close to 5. So this is a point. So from 3, Fourier number 3, you are moving here, and from there you can find out the value of theta naught by theta I. This is 0.6 here, this 0.5, it's a 0.6, 0.7. This will give somewhere around 0.58. So you are getting theta naught by theta I as 0.58. Okay, from the chart, reading the chart, you are getting theta naught by theta I as 0.58. Theta naught is T naught minus TA, that is mid-plane temperature difference. Theta naught is mid-plane temperature difference, that will give T naught minus TA, and theta is the initial temperature difference. Initially it was 225 degrees centigrade and ambient is 25, so it is 200, and this is also known 25, and this is quantity which is required. Theta naught by theta you are getting. So let us go to the next slide. So from Heisler's chart for central line temperature for an infinite plate, we get theta naught by theta I as 0.58. Now you can calculate theta naught as 0.58 into theta I. 0.58 into theta I is initial temperature difference, which is 225 minus 25. That will give 200. 200 into 0.58 will get 116 degrees centigrade. So this is a mid-plane temperature difference. Temperature difference at in the middle plane after 2 minutes, the mid-plane temperature difference is 116 degrees centigrade. So this is temperature difference. So to get that mid-plane temperature, you need to add a TA. So 116 plus 25, that will give 141 degrees centigrade. So the temperature at the center is 141 degrees centigrade at the end of 2 minutes. It has cooled to 141 degrees centigrade. From initially it was at 225 degrees centigrade. It has now come down to 141 degrees centigrade after 2 minutes of cooling process. Okay. So next we need to calculate the surface temperature. This is a mid-plane temperature at the end of 2 minutes. We need to calculate the outer surface temperature at the end of 2 minutes. For that we need to calculate another parameter, x by L. X is the position. At what position we require the temperature, divided by the half the thickness, that is 2L by 2, from the center to the surface, that is this. But here you are asked to find out the temperature at the surface. So that is here I will show. This is a mid plane. Now suppose you want the temperature at this point, somewhere here. Okay, then this is x. From mid plane to that point where temperature is required, that is x. And the characteristic length is this distance. That is half the thickness. So this is L. And where you want the temperature, from the mid plane you measure that distance, that is x. But in this case we want the surface temperature. So from mid plane to the surface the distance is L, and that is x is L. We need the surface temperature, so the distance from the mid plane to the surface is x. That is x is L. Okay. So if it is somewhere inside, then that distance it will be less than L. So maximum x value is L, and that is at the surface, and divided by L. So x is L itself. Here x is L itself because we require at the surface, temperature at the surface. So L by L will get 1. So that ratio position for the position where we require the temperature. So this is a ratio of x by L, which shows the position with respect to the mid plane. So it gives 1. Now we can go for another chart, Heisler's chart, which gives a position correction for temperature for an infinite plate. Correction for temperature. So we know mid plane temperature, but we need to find out the temperature at some other point. Here in this case it is at the surface. So you have x-axis 1 by byte number, and also this is the x by L. X by L 1, 0.9, like different values are there. So x by L in our case it is 1. This is the x by L 1. This lower curve, and the value of 1 by byte number we know it is 4.8. So this is a semi-log graph. So here you have 0.1, then next it will be multiples of 10, 1, and then it is 10, after that it will be 100. So here in between you will have 0.1 means 0.2. This will be a larger gap will be the first. 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 like 1. Then again after 1 increment will be 1. So 2, 3, 4, 5, 6 like that. Here it is 10. Then again this gap will be 10. Every smaller interval is 10. Here all smaller interval is 1. Here all small interval is 0.1. So here we have 1, 2, 3, 4, 4.8. 4.8 and we have 1 x by L ratio 1. From there you get 0.89, approximately 0.89. So that is the value of theta by theta naught. Theta by theta naught. Theta is the temperature difference where you require the temperature. So theta is temperature difference. So what point you require the temperature difference? Here in this case it is on the surface. So theta by theta naught gives a temperature difference at the surface divided by central line temperature. Okay. So from this graph you are getting theta by theta naught as 0.89. Now from the chart we got theta by theta naught 0.89. Now theta is 0.89 times theta naught. Theta naught we know central line temperature difference. It is 116. Multiplying that you get 103.24. So 103.24 is the temperature difference at the surface at the end of 2 minutes. Now you can add ambient temperature which will give the temperature at the surface at the end of 2 minutes. So the temperature at the surface at the end of 2 minutes is 128.24. 128.24. This is the temperature at the surface at the end of 2 minutes. So what was the temperature at the center at the end of 2 minutes? Center temperature difference is 116. We got it from the first graph. Center temperature difference it is 116 and center temperature was 141. So center is at 141 degrees centigrade whereas surface is at 128.24 degrees centigrade. So there is a lot of variation for the temperature from the interior mid-plane to the surface. At the end of 2 minutes, mid-plane is at 141 degrees centigrade whereas surface is at 128.24 degrees centigrade. Nearly 13 degree difference is there. So center is hotter. It is not getting cooled as fast as the surface. Surface is getting cooled fast because convection is happening at much faster rate than conduction. Inside it is providing more resistance to conduction whereas convection is happening fast from the surface. That's why the temperature has not attained uniform temperature. So temperature there is a lot of variation. So this is not a level heat analysis. Now we need to find out the amount of heat transferred from the body in the first 2 minutes. So for that another chart we need to read. So where you need to calculate this parameter byte number square into Fourier number. In the x-axis we will have byte number square into Fourier number. So we have calculated the byte number already known and the Fourier number is also known. Substituting that we will get byte number square into Fourier number as 0.133. Now we will go for the chart. This chart showing the x-axis byte number square into Fourier number, whereas here you have a plot constant byte number plot. This byte number, these values are byte number, constant values of byte number, and here you have that fraction of energy removed from the plate. So x-axis gives byte number square into Fourier number, and here we have constant byte number plot. So our value is 0.133. So it is 0.133. So here it is 0.1. Okay, this is 0.01. So here it is 0.1 and it is 1. This is 0.1. Okay, this is a larger gap. So this is 0.1. So wherever you have a larger gap, next starting, this is a starting point where 10 raised to minus 1, that means 0.1. And this is going to be 0.2, 0.3, like this is 1. Next this is 2, 3, 4, etc. This is 10. Now this is going to be another 20, 30, like 100 you will get. So this is 0.1 and this is 0.2. So this small distance 0.133, this is 0.1 and it is 0.2. So this is 0.133. We have taken 0.133 and byte number is 0.2. That line, 0.2 line I just produced, and from there drawn a horizontal to get this value, that is the fraction of energy lost, 0.45, okay, 0.45. So Q by Qi we will read as 0.45. Qi is the initial energy possessed by the body. At the starting of the cooling, what is the energy possessed? Total heat content of the body in the starting, and Q is the amount of energy removed from the body. So Q by Qi you are getting as 0.45. So from that you can find out Q. So Q by Qi from the Heisler chart for dimensionless heat loss for an infinite plate, we get Q by Qi is 0.45. Now Q is equal to 0.45 to Qi. What is the initial energy content? The starting of the cooling process, no, mCp into delta T, that is the total energy content of the body. It was initially at Ti temperature, ambient was at 25, that is Ti. So Ti minus Ti is the temperature difference into mCp, that will give the total energy content of the body, that is Qi. Initially, what was the energy possessed relative to the surrounding, what was the energy content of the body. So that is mCp or ρVCp into Ti minus Ti. Into that total energy content, 45% has been lost. So that is the fraction what we have got. The fraction of the energy lost, 45. 45% of the heat is dissipated to the surrounding. So 0.45 into ρVCp into Ti minus Ti. Let us substitute for that. 0.45 into density into V volume. How do you calculate? Surface area, one side surface area into 2L. 2L is the thickness. It's not a finite plate I shown, but for an infinite plate also same thing. It is one side surface area into 2L. So A into 2L into Cp specific heat into Ti minus Ti. Now let us substitute for this. 0.45 density is 7850. Area for a surface area, one side surface area, if I take it as 1 for 1 meter square area, if I take this shaded is area, one side area only I have shown, one side area into 2L will give the volume. So if one side area is taken as 1 meter square, I put it as 1 meter square into 2L, L is 0.025, the thickness was 5 centimeter. So L is 2.5 centimeter or 0.125 meter. So L is substituted, and this Cp value 460, the temperature difference. So taking one side area, the unit one side area. Unit area means unit only one side area I have taken. So you get Q as 16.24 megajoule. So in joule converted into megajoule, divided by 10 raised to 6, it give megajoule per meter square. Per meter square of area, one side area, so much heat is lost. So this calculation is based on one side area. But if a convection is happening from both sides, so based on the convection area if you take 1 meter square area, other side also 1 meter square area is there. And convection, since convection is happening from both sides, if you are taking the area means, if you take the convection area, then if you take 1 meter square area here, there will be other side also 1 meter square area will be there, it will be 2 meter square area. So you have to take A as 0.5. If you take 0.5, other side also will have 0.5 and convection area will be 1 meter square. So you can take 2A as 1 or A as 0.5. Here 0.5, other side also 0.5. So totally unit area you will get 0.5 plus 0.5 unit area you will get. Unit convection area. Okay. Whereas this is based on one side area. Per unit, one side surface area, per unit, one side surface area, so much is the heat lost. Whereas if you take convection area, per unit convection area means, here you take half and here other side also half you take, totally 1 meter square area you will get. For that, what is the heat? So putting A as 0.5, you will get 8.1, that will be half of that. So that means, actually, if you take the convection, per unit convection area, so much heat is lost. Okay. So this is the heat lost per meter square of surface area of the plate. Whereas this is the amount of heat removed per unit area, that considering only one side.